Namaste everyone. Welcome to second PUC physics class. We have been discussing about radioactive process, nuclear process. We studied it for 45 minutes in the last class. We have seen what are the things related to it. What are the radiations emitted and what are the types of particles emitted. Namaste, hope you are doing well. Welcome to the class. So, radioactive phenomenon is a nuclear phenomenon. The unstable nucleus may rupture and it can emit alpha particles, beta particles and gamma radiation. When alpha particle is emitted, what happens you have seen. And when beta particle is emitted, what happens you have seen. And in beta particles you have to see one more thing, artificial radioactivity, that we have to see. And when gamma rays are emitted, nothing changes will occur in atomic number and mass number, because they are all just extra energy emitted from the daughter nuclei. Daughter nuclei will have an extra energy, it will be in the excited state, and it comes to the de-excited state by emitting energy in the form of gamma radiation. Okay, now when a parent element emits beta particle, we have seen that, right? Alpha particles are nothing but helium nuclei. 2 protons, 2 neutrons coming out of the nucleus. That is not strange, because already nucleus contains protons and neutrons. But how come the electron from the nucleus? So, what is the equation for beta particle emission? ZXA, emitting beta minus. This is natural radioactivity. If radioactivity is occurring naturally, then electrons will be emitted. How? After the emission, the daughter nuclei formed will have atomic number increased by 1, mass number remaining the same, and you have minus 1 is 0. You can, of course, there is no, usually we don't write electron like this, because we can't assign atomic number and mass number to an electron. This is just to make very simple, so that you can manage the equation easily here, right? It looks very nice, but we don't represent the electron usually, but that is not wrong of representing. Okay, so where we are now? Yeah, now how come electrons from the nucleus? During the process of radioactivity, inside the nucleus, a neutron gets converted into a proton and an electron. And electron comes out and proton remains inside the nucleus. That is why we have lost one neutron, but we have gained one proton. That is why there is no change in the mass number. Mass number has remained the same, because mass number can be obtained from either proton or neutron. Anyone. Nucleons will support for the mass number. So either you have more number of protons or neutrons, whatever it is, mass number will be more. So even if you have lost neutron, we have got one proton. But atomic number is not supported by neutron. So this neutron is, if it is lost, atomic number will not change. But we have got one proton excess, atomic number must increase. So Z plus 1. This is natural radioactivity. But usually these gamma radiations are most powerful. You know that they are highly penetrating. They are used to kill cancerous cells. We use it for constructive purpose. They can kill the cells, but they are injected onto the correct cancerous cell to the particular area, and only that much amount of required dose is injected onto the cells. It is a very careful treatment, but still they are useful. Now the thing is, these gamma radiations, actually what I wanted to say, there is artificial radioactivity. Yes, I forgot on the topic itself. In artificial radioactivity, what is mean by artificial radioactivity? So if you want to treat a person with the gamma radiations, you can't wait for the natural radioactivity to occur, right? You can't wait for take a sample and wait for the radioactivity to occur for a long time, right? Because we don't know at what time it happens. It starts. It doesn't depend on the external parameters. It is a spontaneous process. At any moment it can start. So we need the radioactivity which will start by our control. How to do that? Some of the elements are not radioactive, but they can be converted into radioactive materials. For example, aluminum is not radioactive. We use aluminum everywhere. It is not radioactive because its nucleus is stable. Can't you convert it into unstable nucleus so that it undergoes the radioactive decay? Yes, possible. It can be converted into phosphorus by injecting neutrons into it. So aluminum, which is not radioactive, can be converted into a radioactive phosphorus. This is called artificial radioactivity. But if you do so, then phosphorus will start radioactivity and you can get gamma radiation, But what the particle emitted in that, it is not electron, it is called positron. So what is positron? Positron is the antiparticle of electron. That is what we get in artificial radioactivity. So I'll write it here. So during the emission of beta plus particle, we represent positron as plus 1 E0. Positron is the antiparticle of electron, which has got the same mass as electron but positive charge. Its polarity is opposite to that of electron. Plus 1.602 in 10 to the power minus 19. But mass is same as that of electron, 9.1 into 10 to the power minus 31 kg. So how will be the beta plus decay? If a parent element emits beta plus particle, this is possible only in artificial radioactivity. Remember, this is electron. So beta minus particles are nothing but beam of electrons. So this is called positron. Yes, that is positron. So it emits beta plus, and the daughter element formed will have an atomic number less by 1, mass number remaining the same, plus 1 E0. This is positron once again. Right? So plus 1, you see it is balanced. So when a parent element emits a positron particle, that is in artificial radioactivity, not electron, a beam of beta positive particles, the daughter element formed will have atomic number less by 1 and mass number remaining the same. But when beta minus is emitted, atomic number increases by 1. Now, how come is this one? How come this positron particles from the nucleus? During the process of artificial radioactivity process, during the process of positron emission, a proton gets converted into a neutron and a positron. This is the process. During the process of artificial radioactivity, positron emission, inside the nucleus, so before the emission of positron, inside the nucleus, a proton gets converted into or split into neutron and a positron. Proton lost. If proton is lost, atomic number should reduce by 1. You know it. Sir, we have got a neutron, but it doesn't contribute to the atomic number. It contributes to the mass number, correct? This neutron is contributed to the mass number. But sir, that means the mass number should increase, right? But we have lost one proton, no? One proton, right? So we have lost one proton. That proton was also contributing to the mass number. I think you will get the logic, right? A proton has been converted into a neutron and positron. We lost one proton. A should be reduced by 1, minus 1, correct? But that appears as a neutron. Neutron also contributes to the mass number, plus 1. No change. No change in the mass number. So we lost one proton. No problem with Z. Sorry, there is a problem with Z. Z minus 1. A neutron has come into picture. That doesn't contribute this. Z minus 1 remains as it is. So this is what we have seen. But later on, it was found that these two equations have satisfied the law of conservation of charge, and they have satisfied conservation of mass. Mass is conserved. The mass of neutron and proton and electron, when this is added, you get the mass of neutron. Mass is conserved, charge is conserved, you see. Positive charge, negative charge, combined, neutral. Here, charge is conserved, positive, neutral, positive. Mass is conserved, but energy is not conserved. So this was a question mark for a long time. Why energy is not conserved? That means energy of this plus this is not equal to energy of this. So where that energy has gone? Then it was found that one more particle called here antineutrino is also coming out of the nucleus, antineutrino, along with the electron. So one more particle, and what is its mass? Almost 0. It has no mass, it has no charge, because already they are conserved. It was having some energy. So a particle having almost 0 mass and some with some energy, missing energy, that is coming out along with the electron, that is called antineutrino. What about here? Whether they are conserved? No, energy is not conserved. Everything else is conserved. There is one more particle called neutrino which is coming, and it is an antiparticle of antineutrino. Neutrino and antineutrino are antiparticles. So this is how the equation is balanced energy wise. So you may have a question like this: along with the positron. What is the particle that is coming out carrying some missing energy? That is a positron. Along with the electron, what is that coming? Antineutrino. Now there is a special thing about this antineutrino, positron and electron. These positron and electron are antiparticles. You know that Einstein's mass energy is vice versa is also true. E equal to mc squared. What do you mean by vice versa? Mass can be converted into energy. Give an example for mass getting converted into energy. When you form the nucleus, some mass is lost. That is converted into binding energy. When the nuclear fission takes place, the mass of reactants will be more, mass of products will be less. So that difference is lost in the form of energy, converted into the form of energy. These are all the examples for mass energy relation, mass to energy. Do you have an example where energy is converted into mass? You have some radiations, they suddenly get converted into particles, masses. Do you have an example? Yes. And the example goes like this. I'll rub this. So which is the example for conversion of energy to mass? Best example is electron-positron pair. That is available in nature. Electron-positron is found in nature, but these electrons and positrons will be moving with high kinetic energy. They are antiparticles, remember. One is positively charged, another is negatively charged. And when they come closer, if they join together, they become a gamma ray. Very strange, right? Two particles combining together to form an energy, right? As if when protons and neutrons are combined together to form a nucleus, they lose some energy, they lose some mass and get converted into energy. So, in the same way, an electron and a positron, they can come together and join together, and then gamma ray will be emitted. Now can you tell me for what this is the example? Again, mass to energy. First one, mass to energy itself. Similar to binding energy and fission energy. Mass to energy, because this is mass and this is mass and this is energy. Do you agree? And this type of conversion of mass, that is electron and positron, they are mass particles, they combine together and they destroy themselves and an energy is released. And from there onwards you will get a gamma ray. You don't have any electron positron. You don't have mass. You have energy, packets of energy. That is radiation. Simply imagine, this is impossible. Simply I am giving an example for understanding it. Solar radiations come to you, right? Visible light comes to you. You can feel that visible light. You can see that, and you can feel the infrared radiation. Imagine what will be the case if, how will be the case if all that radiation getting converted into mass, particles, and as they fall, they are particles. So that is a very strange thing, right? So similarly, but that won't happen. So all the radiation, there are certain conditions. If an electron and positron particles combine together to produce a gamma ray, there is a condition. That electron and positron should have some amount, a minimum amount of energy. Only if they have certain kinetic energy, then only they can combine. That is, the kinetic energy of this is 0.51 million electron volt and kinetic energy of this is 0.51 million electron volt. If the kinetic energy of, I am putting not in joules, I am putting it in electron volt. If the kinetic energy of this is minimum kinetic energy of this is so, if it is more, no problem. If it is less, this can't happen. So one electron, another positron having a minimum kinetic energy of 0.51 million electron volt, if they combine together, they produce a gamma ray, and the energy of the gamma ray is 1.02 million electron volt. You add this, you'll get this. This is called pair annihilation. Pair annihilation. So what do you mean by pair annihilation? Two electrons and positrons combining together to form a gamma ray, and mass is lost, energy is obtained, mass to energy conversion. This is called pair annihilation. The minimum energy required for this is 0.51 million electron volt. Now the reverse is also true. What is reverse? A gamma ray under suitable condition can split into electron positron pair. That is what I have given the example. I gave that example earlier itself, right? I should not have given that example here. This is mass to energy. This is quite it is quite simple, because you have seen binding energy, mass of some uranium and products and reactants difference that can getting converted into energy. This is common. Okay. Now here I should have given that example. Some radiations coming towards you, suddenly it is getting converted into mass. Energy to mass conversion. Second one, energy to mass. Gamma ray splitting into electron positron pair, that is also possible. When a gamma ray of energy minimum 1.02 million electron volt, and if the energy is not less than this, this is not possible. If the energy is more than this, of course it is possible. A gamma ray photon of energy more than 1.02 million electron volt or equal to 1.02 million electron volt, under suitable conditions, it can split into two particles. One is electron and another is positron, and these two will have energy 0.51 kinetic energy, and they move like this with this kinetic energy. This is called pair production. Energy is lost, a pair of particles and antiparticle is produced. This is pair production. So this is continuously happening in nature. Electron positrons will combine, gamma ray is produced, mass to energy, and gamma ray will split into electron positron pair, and energy is converted into mass. So if you are asked to write an example for mass to energy conversion, it is pair annihilation. Try to see that. Mass to energy conversion, it is pair annihilation. Energy to mass conversion, pair production, because finally you should get mass in your hands. You should have mass, final product. Mass, electron positron pair from the energy, packet of energy, that is radiation. So mass to energy is energy to mass pair production, mass to energy, that is pair annihilation, destruction. Annihilation means here destruction. So that is one more thing, and actually it is not in the syllabus, but you can see this. It is not very tough. You can remember these values. Suppose you have some 1 mark question, because nowadays in the theory question paper also, question paper setters have started asking some tricky questions, 1 mark questions in between, 1 or 2 questions, so that everyone shouldn't score 100. That's what the aim is, because scoring out 100 out of 100 should not be so easy. Yeah. Right. So that is about that artificial radioactivity and natural radioactivity. So for artificial radioactivity, we should convert a non-radioactive substance into radioactive substance. Now we will see decay law, radioactive decay law. What is decay law? Decay means disintegration. Decay means decreasing. Decay law. Now, decay law says that, now suppose you have taken uranium, say 1000 atoms of uranium. Today you have taken 1000 atoms of uranium. By the end of this day, evening, say you have only 500 atoms. That means 500 have been lost. So 500 are lost. Then what about tomorrow? By tomorrow evening, will remaining 500 will be lost? No, because by tomorrow evening all 500 will not be lost. Only 250 will be lost. That is how it decays. So rate of disintegration, that is what you call rate of decay, rate of disintegration, rate of disintegration, or rate of decay. Same sentences. That means how many numbers of atoms have been decayed per second. It need not be calculated per second only. You calculate how many number of atoms have changed from uranium to thorium in 10 seconds and divide it by 10. Then you will get per second, right? The number of atoms that have been decayed, dn, decreased per second, dt. For example, n is the number of atoms remaining in the sample in t seconds, 0 seconds, say. When I started, I had 1000 atoms, right? 1000 atoms of uranium are 1000 uranium atoms only, correct? All are uranium atoms, pure uranium. Radioactivity started. Early morning radioactivity started. By the end of the day, I have only 500 uranium atoms. Sir, what about remaining 500 uranium atoms? They have been converted into thorium. They have emitted alpha particle. Now they are not original uranium atoms. Their atomic number has decreased by 2, mass number by 4. Now I can't call them as uranium. They are thorium. So pure uranium are only 500. Remaining are thorium. So how much it has decreased? 1000 minus 500 in how much time? 24 hours. And convert it into seconds. That is, if n is the number of atoms in the sample in 0 seconds, pure atoms, original atoms, and after the decay has started, in t seconds, let the number of atoms in the sample be n minus dn. What is dn then? dn is the decreased number of atoms. How much has been converted? So what is the original number? N minus dn. Right? dn number of atoms are lost. 500 are lost. How much remaining? 1000 minus 500. That is 500. Then dn is the lost number. This is called rate of disintegration. Can you understand it now? 500 atoms have been lost as thorium divided by 24 hours. Convert it into seconds later. Rate of disintegration is the number of atoms disintegrating per second. In 1 second, how many atoms have been converted from uranium to thorium? Uranium to thorium is just an example I am giving you, right? That may be any radioactive material. It may be radium getting converted into another material, anything. So, the rate of disintegration is the number of atoms disintegrating per second. If you divide it by any time, it comes to the answer of per second. And what about radioactive decay losses? So, you must be aware of this definition clearly. Number of atoms disintegrating per second, it says it is directly proportional to dN by dt is directly proportional to the number of atoms in the sample at that instant. How much number of atoms you are holding now? Accordingly, the rate of decay will move. The number of atoms disintegrating per second is directly proportional to the number of atoms in the sample at that instant. How much you have now, accordingly the decay will go. If you have more number of atoms, then the decay will be very fast. If you have less number of atoms, decay will be less. It is as if you read for the exam. Do you have, of course, it is opposite to the way in which you read for the exam. If you have more number of days, holidays remaining, you read very slowly. Because your preparation is very slow, because the examination is approaching and it is having too much length of time and you will have to wait for many days for the exam. Reading will be slow. It is reverse of this decay law. Tomorrow itself is the examination. Today we will be reading like anything, because so many chapters are left and somehow you have to score, otherwise you will be put in trouble. So somehow you have to do well in the examinations. So today nobody can talk to you. You will be preparing like anything. Okay, so like that. But here, if more number of days are remaining, you will be reading like anything. And when you are approaching closer and closer to the day of examination, you will be reading lesser and lesser, like that. If you have more number of atoms in the sample, decay is very fast. If you have less number of atoms in the sample, decay is very slow. It is as if, one more example I can give. Suppose I have some money in my pocket. I have a principle in my life. Every morning, whatever I have in my pocket, I give 50% of the money, what I have in my pocket, I donate it to others. I just donate it to others. If I have such a habit, what is the amount of money that I will lose every time when I donate it to others? That directly depends on how much money I have, isn't it? Because you see my sentence, I donate 50% of the money that I have to others. Means, how much I will donate to others? That depends on how much I have. Today I have 1000 rupees in my pocket. When I get up in the morning and when I start, I find that there is 1000 rupees in my pocket. When I come out, whomever I meet, any beggars or somebody else who are very poor, I donate them. How much I should donate? If I have 1000 rupees, I will donate only 500 rupees. I will donate 500 rupees to different people. Next morning when I get up and when I start, I have only 500 rupees in my pocket. Should I donate all the 500 rupees? If I donate all the 500 rupees, what is the meaning? I have donated 100% of my money. No, I should follow the same principle. What do you mean by that principle? That is, I donate 50% of the money that I have, correct? And the amount that I donate is directly proportional to what the money I have then, because 50% of the money that I have. Now I have only 500 rupees. So what should I donate? 250 rupees. That's all. That means the amount that I donated today is less, 250 only, because I had only 500 rupees. Yesterday I had 1000 rupees, so I donated 500. That means what I donate depends on what I have. And after the second day, third day, I get up, I find only 250 rupees in my pocket. I donate 50% of that. That means I donate only 125 rupees. That means the amount of money that I lose every day after donation is directly depending on how much I have in my pocket. Correct? The amount of money that I lose every day, per day, depends on how much I have in my pocket on that day. If I have more amount of money, suppose I have 1 lakh rupees in my pocket on one day, I may donate 1 lakh means 50,000 rupees on that day to others. That's how it goes. That means radioactive decay law says that the number of atoms disintegrating per second is directly proportional to the number of atoms in the sample at that instant. If you take huge number of uranium atoms, on that day the activity will be very, very high. And this is called activity. What do you mean by activity of the sample? Number of atoms disintegrating per second is called activity. That, remember, I may use that word again and again. So rate of disintegration or activity. How many number of atoms are disintegrating per second? That is called activity. So rate of disintegration is directly proportional to number of atoms in the sample at that instant. Of course, if it is so, of course, this rate of disintegration, that is number of atoms disintegrating per second in any sample, of course it depends on the number of atoms in the sample, and also it depends on the sample. Suppose if I take 1000 uranium atoms and 1000 radium, will radium atoms get converted into some other atoms same as uranium? No, it depends on the sample also. Some samples decay very fast. Some samples decay by taking a long time. For example, carbon 14. It is, you might have studied it in biology class. Carbon 14 is used to find out the age of fossils, right? By studying the radioactive decay. Carbon takes many years to get reduced, decayed. It emits alpha, beta, gamma rays, alpha, beta particles and gamma rays very slowly, and it gets changed into some other daughter nuclei very slowly. Some other atoms decay very fast. There are some varieties of samples. Some have their decay rate very fast. They decay in seconds. Some decay in thousands and thousands of years. All are useful for us. Every element is useful because we made it useful. Now that means dN by dt, if you want to put it is equal to, you should bring a constant. That means that constant should be different for different elements. That depends on how fast they decay, how fast they change their characteristic. Minus lambda n. So two people came into existence here. One is minus, another is lambda. What is lambda? Lambda is a constant called decay constant for that material. Lambda is a constant called decay constant. And why negative? Negative sign shows that the number of atoms are decreasing. You can bring this negative here also, minus dN by dt, and keep this positive. You can do that, right? When you bring that minus here, minus dN by dt, because number of atoms are decreasing with time. You don't have radioactive growth. You have radioactive decay only. Atoms, you take 500 uranium atoms today, tomorrow by the time you count it, you have 1000 uranium atoms. It has grown, it has given birth to some small kids. Not possible. Radioactive growth is not found, it is only decay. Whereas cancerous cells are multiplying, right? So cancer, they are increasing, whereas here we have only decreasing. That's why minus sign. So negative sign indicates that number of atoms in the sample goes on decreasing with the time. Lambda is a constant called decay constant. Sir, you give a constant for material, decay constant of carbon, decay constant of radium, decay constant of uranium. What does it mean, sir? If decay constant is more for a material, what do you mean by that? It decays faster. It takes less time to decay, very fast decay. And if decay constant is more, it decays faster. It takes less time to decay. If the decay constant is less, it decays very slower. In order to indicate whether the material decays very fast, that means gets converted into some other daughter nuclei very fast, then lambda is very high. If lambda is very low, decay constant is less, that decays very slowly. Carbon decays very slowly. It takes long time to decay. Lambda is very less. whereas some other materials decay very fast and their lambda value is very high. So decay constant, we will define what is decay constant very properly later. So it is a constant, it is a number which determines whether that material decays faster or slower, right? Okay, now we will move on to an equation, very important equation. How is the equation? Right. Now, I want an equation which gives you the number of atoms in the sample after a certain time. Now, for example, I have an equation which gives the distance traveled by the particle after certain time t when the acceleration is uniform. What do you mean by acceleration uniform? The particle increases its speed by same amounts, right? For example, a freely falling object, its velocity is increasing by 9.8 meter per second every second. Every second, after 1 second, 9.8 more. Next second, again 9.8 more. A particle moving with uniform acceleration. What is the distance traveled by the particle after t seconds? What is the velocity of the particle after t seconds? V is equal to v naught plus at, x equal to v naught t plus half at squared. But remember, all these are equations for a straight line. But radioactive decay is not a straight line. It is not a straight line. It is called exponential decay. What do you mean by exponential decay? It's a different type of decay. We will see that. Now, that means if I have n naught as the number of atoms in the sample at 0 seconds, okay, 0th second I have n naught number of atoms in the sample. N is the number of atoms in the sample after t seconds. Definitely n is less. I have 1000 atoms today. By the end of the day, after 1 day, I have only 500 atoms. So after 1 day, I lost 500 atoms. N naught minus n. That is after 1 day. So n is the number of atoms after t seconds. That is original number of atoms. I'm not talking about what is lost. Originally present. How many uranium atoms are still present by the end of the day? 500. That is n. N naught is the original number of atoms. Now this is atoms, original atoms, but after t seconds. How can you relate all these things? And lambda is called decay constant. Lambda is a constant for the material and is called decay constant. Now tell me one equation which will give you how many number of atoms will present in the sample after t seconds if n naught is the original. What may be the velocity of the body after t seconds? V is good, but that is a straight line because the acceleration is uniform. If acceleration is uniform, Vt graph is a straight line. But it is not a straight line here. Number of atoms versus time is not a straight line. After t seconds, what is the number? That is what I want to get it. That is the derivation. Now start from the decay law. What does decay law say? Decay law says that the rate of disintegration, that means how many atoms decay per second, how many atoms lose either alpha particle or beta particle or gamma ray. Of course, mainly alpha particle and beta particle, not gamma ray. How many alpha particles have emitted alpha particle and, how many original atoms have emitted alpha particle and beta particle, that by changing themselves to different characteristic, different element, how many of them have lost dn? In what time dt? What is the activity? Rate of disintegration is directly proportional to the number of atoms in the sample. How much money you have donated? Directly proportional to how much you had in your pocket in the morning, because you 50% you will donate. And dn by dt is equal to minus lambda n. Lambda is a constant called decay constant, and n is the number of atoms in the sample after t seconds. Okay, now we will rearrange it. Dn by n. We will take dn by n together because we are going to integrate this. Dn by n is equal to minus lambda dt. Dt here, n here. Dn by n is equal to minus lambda dt. Now shall I integrate this? And people who don't know integration, take it granted now. Just follow this, because after studying integration, you will come to know what is this. We will integrate it now. Integrating on both sides. Okay? Integrate it from, the number of atoms have to be integrated from n to original n naught, starting initial point n naught, this is n. Right? And this is 0 seconds, t seconds. When the time is 0 seconds, number of atoms were n naught. When the time is t seconds, only n number of atoms were original. Rest of them have decayed. So they are not original. So rearrange it, dn by n. dt you will take it. Integrate this from 0 to t seconds. Integrate this from n naught to n. So what you will get? Now if you integrate this within the limits, what is the integration of 1 by n? You know differentiation of log n is 1 by n, right? D by dx of 1 by x is log x. Integration of log x is 1 by x. Difference d by dx of log x is 1 by x. So what is the integration of 1 by x? It is log x. And you have one more logarithm, log to the base e, right? Ln, we call it as ln. So what is 1 by n? Ln n. Ln n. And limits we write it here, n naught to n, right? Original number of atoms to n number of atoms. Okay? Is equal to, hope you have followed this. Integration, those who know integration, you can do this. Others leave it as it is now. Because you will study, after studying integration, this is nothing. This is very simple, basic formula. So you need not worry now. If you have followed integration already, you can do that. So dn by n, 1 by n integration with respect to dn is ln n, that I have written. Limits n naught to n. What is the integration of lambda? Lambda is a constant. So you have 1 here, lambda into 1 into dt. So what is this? Minus lambda t. Of course, I can write lambda outside because it is a constant. Minus lambda. Integration of 1 with respect to d time is t and 0 to t. Correct? So these are all constants. Integration of 1 only. Minus lambda outside the integration because it is a constant. Integration of 1 dt, it is t. Because differentiation of t is 1. So integration of 1 is t. Okay, put the limits. Upper limit ln n minus ln n naught, upper minus lower is equal to lambda into minus lambda into t minus 0, upper limit minus lower limit. That is lambda t. Now you know log a minus log b is equal to log a by b. You know that formula. Log a minus log b is equal to log a by b. Here it is ln, log to the base e. Ln n by n naught is equal to minus lambda t. Now the method of bringing ln here, it is like this. N by n naught is equal to e to the power minus lambda t. This is how do we write. N by n naught is equal to e to the power minus lambda t. So what is n is equal to? N is equal to n naught e to the power minus lambda t. If n is equal to n naught e to the power minus lambda t, this is the equation which governs the number of atoms in the sample after t seconds. So n is equal to n naught e to the power minus lambda t gives the equation which gives the number of atoms in the sample after t seconds. So I hope you have followed this, right? So this is dn by n and minus lambda into 1 into t. After integration 1 by n is ln n and you have put the limits and integration of 1 is t, lambda t. Of course, if you have not followed this exactly, don't worry because you are after integration, studying integration in mathematics, you will definitely follow this. Ln n minus ln n naught minus lambda t. And if you bring ln to this side, it becomes e to the power because it is log to the base e. So n by n naught is equal to e to the power minus lambda t. Right. So this equation gives the number of atoms in the sample after any time t seconds. This is an exponential equation, e to the power. Okay, I can write this as e to the power like this way also. So e to the power x is an exponential function. How does it vary? As if you have log x, 1 by x and all. This is another function, right? Square root and all. This is a mathematical function. We will see what is the meaning of e to the power in another class. Just worry about how this equation is obtained. We will study the details of this equation. How does the graph vary? How does the number of atoms? How does the number of atoms change with the time? And all those things in the next class. So thanks for watching my class. We will see the more aspects of this in the next class. Thank you.